Okay, hello everybody. Yeah, I'm very happy to introduce Dr. Tim Flohrer, who is the head of the Space Debris Office of the Space Safety Program Office at European Space Agency. Yeah, he will give a talk about the space debris problem, a challenge to further space exploitations in today's colloquium we are having here. Yeah, just to give a short introduction about Tim Flohrer and his career. Yeah, he's looking back actually on approximately 20 years of experience within space debris science. So basically, in 2002, he joined as a research associate at the AIUB, the Astronomical Institute of the University of Bern in Switzerland. He was there involved in ground and space-based optical surveillance, space surveillance and planning and processing of software. Yeah, then in 2007, he joined ESA's Space Debris Office as an engineer. 2009, he became a space analyst. 2014, he joined ESA's Space Situational Awareness Program, SSA, and Space Safety Program, S2P. Yeah, he was basically addressing and the monitoring of space debris and operational collision avoidance activities for ESA and third-party missions, for example. Also involved in re-entry predictions, mitigation analysis, and also long-term predictions of space debris environment and space debris risk assessment. Then 2018, he became a senior analyst, and now since 2020, he is actually the head of ESA Space Debris Office. In addition to that, yeah, he has several memberships and functions. He is an ESA delegate to the IADC, Interagency Space Debris Coordination Committee, also involved into the IAA, International Academy of Astronautics, the Committee on Space Debris, yeah, and yeah, some other memberships and functions. Yeah, just to give an overview of our connections we have to IWF and especially Lustbühl. Yeah, we are involved in satellite laser ranging and also, of course, space debris laser ranging. There were some recent success in daylight space debris laser ranging. Then some additional synergies between the Space Debris Office and IWF are single photon light curves to, for example, tumbling space debris objects, and also the tumbling analysis of such space debris objects. Then, yeah, there's also the IWF is also part of the Expert Center. And yeah, actually also we are currently involved into the development of laser and detection packages for the new ESA SLR station, which is located on Tenerife. So just for the talk itself, feel free to post questions in the chat. I will try to collect them as best as I can during the meeting, and then read them out and forward it to Tim during the talk or after the talk. And yeah, Tim, let's start with your talk, and basically the stage is yours then.
Yeah, thank you very much, Michael, for the kind introduction, and it's an absolute pleasure to be with you in the virtual world in today's seminar. While I'm sharing the screen, let me say that for the question in the chat, I cannot see the chat while presenting, so I really rely on Michael to handle that, what you write into the chat. But okay, now if you go full screen, we should be ready to start. And Michael, I can't see you anymore, but you can certainly confirm that we are ready on your side.
Yes, I can confirm that I see the screen.
Wonderful. Right, so as Michael already introduced, this is a seminar where I try to introduce you into the space debris problem. Something, as you heard, I do it for quite a number of years and a significant part of my career. And why we here at ESA think it's a challenge to the further exploitation of space, and in particular why we think we should see space as a resource. This for the general topic. I will introduce also the space safety program that we are running now here to you. And then, as you can imagine, and as already introduced, I would dedicate a larger part of my talk on this precise question, how laser technology can contribute to finding a sustainable solution for the space debris problem Right, so I'd like to acknowledge a few colleagues that have contributed directly to this talk. Of course, there's a larger team here at ESA dealing with space debris, but for this talk, I would very much acknowledge Andrea de Mira, Beatrice Gillette, and Emiliano Cordelli, all working here at ESOC, where I am. This is in Darmstadt in Germany. It is also the home of the Space Safety Program and the Space Debris Office. Right, so as said, let's start with the problem of space debris, then the Space Safety Program, and then 3 topics on laser ranging, and in particular, what we did and want to do with the IWF. Right, so a scientific presentation has to start with definition. And for space debris, a definition exists, but it's a technical definition. And it is here, it's all man-made, maybe you should say artificial objects, including fragments and elements thereof in Earth orbit or re-entering the atmosphere that are non-functional. This is a definition given by the IAA, and it's already a few years old and is still valid, but it's very technical and it's not a legal definition. For legal questions, such a definition does not exist. Yeah, and the key point is non-functional. So, and where does space debris come from? Space debris, as it relates to artificial objects, can always trace back to our launch activities. And if we look back in history, we do spaceflight now since 1957 with Sputnik 1. And since then, we see around 6,200 successful launches. And as we will see in a second, these are not distributed linearly over time. There are some peaks, and in particular, there's a very recent peak building up. And yeah, and we have something called space surveillance systems on ground, but also in orbit. And these network of systems of radars and telescopes help us to track the known objects and to build up so-called catalogs. And from those, we know that there's not only upper stages and satellites in orbit, but also many other things, and that is space debris. We have made an animation some time ago where we showed how this aggregation of space debris population went over time. And you see, this is real catalog data, how this built up. And you can definitely see 2 main areas in the near Earth space that are particularly affected by space debris. These are the low Earth orbits, everything up to 2,000 kilometer altitude, and something that you see here as this ring-shaped structure, which is geostationary orbit at 35,800 kilometer altitude above the equator. And everything in between also is subject to space debris, but the density of objects is much lower there. And yeah, this is a reflection where we do our missions. It's like on ground, you find most debris where you have most of the traffic and most of the use of the environment. Yeah, so as I said already, we have sources, and the main source is everything we launch. But then something happens in space. This is unfortunate. These are so-called fragmentation events, and we can discriminate 2 types of fragmentation. These are explosions and collisions. And explosions, everything that comes from intrinsic energy sources, like leftover fuel or not discharged batteries, that causes a rupture of the structure and the creation of many fragments. In the worst case, but sometimes only a few, but in some cases also hundreds or thousands. And then we have collisions where 2 intact objects or an intact object and a fragment or even 2 fragments collide, and that's a collision. And this, due to the high orbital velocities and the energy that is then contained in the collision event, leads to usually a complete destruction. We call it a catastrophic event of the progenitor objects. Then we have other sources, and SRM is an abbreviation for solid rocket motors. Solid rocket motors are firings, and that create residuals like slag from the nozzle cone, or also dust. And then we have something called sodium-potassium droplets, something that is specific for a certain type of ocean reconnaissance satellites of particularly of the Soviet Union, where they ejected a reactor core, and then the coolant liquid leaked out and formed droplets in the environment. And then we have something, everything that peels up from surfaces of satellites, from the foil, from the multi-layer insulation foil, but also from other surfaces, and that creates also debris objects. Yeah, and where does it go? We have, fortunately, the atmosphere helping us to get rid of space debris, at least in the lower parts of the orbits. There is the atmospheric drag that leads to a decay. Lunisolar perturbations can also help, and also solar radiation pressure to put objects down. But unfortunately, this only works in, it takes time first, but only works in the lower parts of the atmosphere. And in GEO, for instance, that I showed before, space debris generated there will literally stay there forever. So what we can also do, we can take out objects, where we could do with the shuttle. This is no longer there, and we could also do active deorbiting, so firing the thrusters so that objects re-enter in a so-called controlled way. What we are developing, and we will hear more about this in this talk, is also getting there and doing so-called active removal, means robotic mission, grabbing a piece of space debris and return it to burn up in the atmosphere. Yeah, so you can imagine that from the tracking that I introduced, we only know about the larger part of the population, and the smaller objects we have to model statistically. And there's something I would like to introduce here. That is our ESA space debris environment model called MASTER. And for those, we actually have a database of all the events that we think may have generated space debris. And this database is then used to propagate the environment, first to model the events, but then to propagate the resulting fragments. And then we use ground-based observations of sensors to validate the modeling. And we also use then surface impacts by either dedicated sensors or also by return surfaces. So we had the opportunity to inspect the solar rays from the Hubble Space Telescope, for instance, when they were brought back by the shuttle and other scans, then to validate whether our model predictions fit to the observed reality. And that is something we do for MASTER. And of course, the environment is evolving. The measurement technology is evolving. That means such a model needs to be kept up to date and validated, reflecting what's happening in the environment. Yeah, so if you now come to the different sources and different sizes, everything in the top right corner called your TLE background. TLE is an abbreviation you should not worry about, but this is the larger fragments, what is in the catalog. So everything larger than 10 centimeter, maybe in the lower part, even now we can be sure that we also have 8, 7 centimeter objects is there from the fragments. Then meteoroid background is in MASTER, but of course these are natural objects. These are not space debris, but we still model them. And then we have also smaller fragments. Then they can cover the entire size range. We have the so-called these droplets of sodium, potassium in the centimeter or millimeter size regime. Slag from the rocket motor firings is also something that covers a few centimeters to micrometers. And the dust, of course, is in the micrometer regime. And the surface degradation from the MLI foils is in the centimeter, decimeter. Sometimes even larger pieces can peel off. So even we have observed also several meters that have been released objects. And then we have from impacts by either natural objects or space debris objects, paint flakes and ejecta, all in the millimeter or smaller size regime. And then how much of those do we know? Well, the bottom right side is everything we track. This is the catalog fragmentation. So looking up the American catalog, today we know about 30,000, a bit more than 30,000 objects. And if you break them down, roughly 2/3 are fragments, so in gray here. So these are resulting of explosions or collisions. And then we have something that was released intentionally, so mission-related objects. We have rocket bodies. These are yellow and for some reason not labeled here. About 2,000. And then we have inactive satellites. Today we count 2,800, and we have active satellites. And this is an interesting fact, because over many years I've always said we have around 1,500, 1,600 active satellites. And this was true until, let's say, 5 years ago. But since then, a revolution set in. We have now these large constellations being deployed, and we have also much more smaller smallsats, CubeSats that are released, so that we can say the active number of satellites is fastly growing. So we have now 5,000 satellites. And if you look now at this diagram, we have definitely more active satellites and inactive satellites. Yeah? And soon we will reach the point that we have more active satellites in orbit than the count of all satellites that are inactive or have already re-entered. This is a rapid change, and this will continue this trend. We are now launching more than 1,200 satellites per year. 1,300 roughly were launched last year. Okay, so this is for the catalog population. Then going to the center diagram, this is then something from our model for master. So we know of about 1 million objects larger than a centimeter that are not cataloged. And then if we go to the top right diagram, this is something larger than 0.1 millimeter. We have then literally billions of objects. And this is the situation in orbit. What can they do to the satellite? So why should we worry? Well, let's look at this diagram then and start again from the bottom right corner. If you have a collision with a tracked fragment of, let's say, a few centimeters, then of these 30,000 that I introduced, then such a collision will lead to a structural failure of your satellite, and the result will be a cloud of fresh debris. So the environment will be contaminated by that. If you go smaller than to the centimeter objects, these 10 centimeter, these one centimeter objects, these 1 million, they can, under some conditions, terminate the mission. They will probably not create too many fragments, but they could kick out a critical piece of hardware on your satellite. It could damage the payload or something like this, and this will lead to severe consequences for the mission, but not for the environment. And if you go to the smaller pieces, the millimeter and smaller ones, there are several effects that can happen. Of course, it destroys surfaces, and there are many of these impacts happening. So the performance gets lower. Electric components can be affected. So there's a multiple of events that can lead to some anomalies in orbit. Right. And one of those I can share here. That's happened to one of the satellites that we are operating here at ESA, satellite Sentinel-1A. It's actually a satellite of the Copernicus constellation that we operate for the European Commission here. And in 2016, we observed that we had a sudden power loss of about 5%, but also saw changes in the satellite attitude and also in the orbital energy, so in the height of the orbit. And then we could benefit from the fact that we had a small camera on board that could be activated. It was actually there not to wait for space debris. No, it was there for checking the unfolding of the solar array. And well, we could reactivate this camera again, and we found then this, what you see here in the middle solar array, this dent is a feature of about 40 centimeter diameter. And from the processing of all the indications we had, we could trace it back to an impact of roughly a 1 centimeter object. And it's also worth to mention here that 7 larger fragments from the backside of the solar array probably have been released that could be tracked, so they were larger than a few decimeters actually. Right. Yeah, and then if you want to visualize how much energy is there in a 1 centimeter object, you can do these so-called hypervelocity impact tests. And what you see here is something I would usually show in person to you, but now you have to bear with me that I only can share a photograph. It's a block of massive aluminum. It's about 12 centimeter thickness. And this little sphere you see in the crater in the middle is 12 millimeters diameter. And that was accelerated to several kilometers per second and then hit this block of massive aluminum. What then happened, of course, is that the aluminum sphere did not survive that. So this is a mock-up. But then a shockwave propagated through the block and ripped off a part of the structure from the backside. And then, yeah, and of course, the energy was transformed into liquidization of the surface and formed this crater on this material that came out of this here. And that's, I think it's pretty impressive. You can imagine the block weighs around 3 kilograms. If you hold it in your hand and you see what a small bullet of only aluminum can make to such an object, then you can imagine what it could do to your satellite if in orbit. Right. And also for other smaller pieces, the servicing missions to the Hubble Space Telescope also confirmed effects that are predicted for space debris, like a penetration in the antenna on the left-hand side, or penetration of the solar array that you see on the right-hand side. And those actually were returned, and they were inspected on ground, they were scanned, and material was extracted, and that helped us very much to understand the population there. Yeah, and then you may ask, okay, so I'm concerned now, but how long do these space debris objects stay in orbit? Well, that you can model, and it depends very much, of course, on the altitude. So if you now take, for instance, 800 kilometer, which is a densely populated region, and check the orbital lifetime, you will see it depends very much on the area to mass. And the ratio of area to mass is very different of satellites and to debris. And you see that large, massive objects can stay there several decades, up to 100 years, while the smaller pieces go down relatively quickly within years, a few years only, even weeks or days if they are just dust. And that you see also in the catalog. This is nicely confirmed by the data we have in the catalog. In blue, you have everything that is there, and in gray, you have what has been taken out. And you see nicely how the atmosphere washes out everything to up to 700, 800 kilometers. And that becomes relevant when we talk later about space debris mitigation. And there is a rule that everything that goes into low Earth orbit should re-enter in a way after 25 years maximum. It's a famous 25 years orbital lifetime limit. Well, that means if you build a small CubeSat, then it actually defines your maximum altitude. That is roughly then around 500, 550, 600 kilometers, where you can go if you do not do active deorbiting, for instance. Yeah, and then what happens if you re-enter? It's quite spectacular, and I have to admit, even doing this for quite a few years, I have never witnessed such an event. And that's something that was known before. It was a controlled re-entry. It was ESA's ATV, Autonomous Transfer Vehicle, that was brought to re-enter over the uninhabited area of the Southern Pacific Ocean in 2008. And so there was an aircraft there. It was really there to film the event so that we can get data out of the demise process there. And that's quite interesting and helping us to build also spacecraft using materials and technologies that make sure nothing arrives on ground, because space debris at the end can lead to on-ground risks. And that we'll see in a second how this could look like. It could look like this if you use materials like stainless steel, titanium. These are, or maybe specific glasses of payloads. They are made to be very stable, rigid, and not subject to thermal degradation. And of course, then in the case of a re-entry, they may survive. And that's why there are limits for the on-ground casualty expectancy. So those things do not happen anymore in the future. But of course, the things that are up there, they are designed in the way they were designed maybe in the 60s. Yeah, so coming back to the space debris population, what we can observe. You saw that in the catalog, we have everything up to the centimeter. So this is on the right-hand side in green. So this is what we can see. And we use radars in the low Earth orbit, and we use passive telescopes in the geo region, in the high altitude orbits. And then everything we do with impact sensors, you see in the left-hand side, is in the micrometer regime. But what we do not have, and what is a very critical gap, is everything in red in the middle. And that's the millimeter to centimeter population, where we have no sensors to access this population. But if you think back, these centimeter objects may have quite a risk, maybe quite a risk to the satellites. So they have to be modeled precisely in order to design your mission properly and protect it and estimate the risk potential. So what we need, and that's a call for ideas and also for technologies, is we need to access this red area in the middle. And yeah, I come to this in a second. And one thing which is particularly interesting, I think, for you there in Graz, and we hear more about this in the later part, is what you can do with laser ranging. It's a relatively new technology when it comes to space debris. And what you see here is something that is very fresh news, and in particular. Yeah, Michael and Georg, please take note. This is fresh from Tenerife, where we just have now accepted our testbed station using an Austrian telescope as well, and to be further accelerating the use of technology for debris tracking. We want to go further in something we call momentum transfer of photons, and I will say more about this in a second. Okay, now, but first, going back now to what we can do about the space debris problem. One thing is, I said already, is to try to avoid the consequences. And before you go on avoiding consequences is to mitigate the creation of space debris. And there are so-called mitigation measures. And if you group them by diameter, you see that for the larger objects, those that we know, that we track, we can do collision avoidance, so that we avoid to crash into those objects and create more debris. And collision avoidance today is standard practice for all spacecraft operators. Yeah, it's a new also commercial business. And what you can also do is then, of course, properly dispose your satellite at end of mission. But it may still take time to get to such a disposal. As I said, 25 years in LEO are allowed, and in GEO there is allowed to go into so-called graveyard orbit. Until you get there, you still have the potential to explode. That's why you have to passivate your satellite at end of mission. And for the smaller objects, of course, these surface degradation that you see there, it can only be prevented if you use, of course, material that does not degrade that much. But okay, there you have to research first, and to limit the exposure time to space. And for others, like the solid rocket motors, yeah, stop doing it or go to other propellants that does not form this slag. You know, that's what you can do, and it's in so-called mitigation guidelines. But still, if we continue with the business as usual, and you see the clock ticking at the bottom right, and then there's a diagram showing the object count. It's not a count of COVID cases, but now it looks a bit similar these days. And everything that pops up in red in the animation is a fragmentation event that leaves a cloud there. And that's a model of the future environment as it would look like after 200 years if we continue in a business as usual scenario. And what you see is, and that now everybody knows these days, is an exponential growth. And that is definitely not sustainable use of space. And that is what we need to avoid. And the business as usual scenario is leading into a space debris catastrophe if you continue like this. Yeah, so why that? Well, if you start in this circle here, you see that the costs of dealing with space debris, to protect your spacecraft, to do collision avoidance, they will increase. And this will accelerate first in these highly populated orbits. And that means the population will undoubtedly grow, as we saw in the animation. And what then will happen is we have then fragments created by collisions that causes feedback collisions, so secondary collisions. And that will even more accelerate the object population. And that was something that Donald Kessler of NASA predicted already in '74 in a paper. And that's why it's called the Kessler syndrome, despite he's not very happy that the syndrome is named after him, but this is what it is. Right. Good. And yeah, to show that this has reached the awareness in an XKCD comic that compares scariness of name and scariness of thing it refers to, the Kessler syndrome is quite prominently located at the top here, as you can see. Okay, so we have seen that our current behavior or business as usual is not sufficient. And over 200 years, we see an increase of the object count in LEO to reach 100,000 if you continue as this. So if we do passivation, this is the light blue curve, we would mitigate about half of the growth, but we would still lead to more than 50,000 objects in this case, and there's still an exponential growth. And I have to say that the effect of the large constellations has been excluded from this propagation. So this is just something assuming that the large constellations do everything perfectly, so they are neutral to the environment. This is not sure yet. I mean, we just don't know. I mean, it could be, but it could not be. Well, so we have to be prepared also for for going beyond passivation. So if we now do correct post-mission disposal, this is the green curve, and have a success rate of 90%, something that we think is realistic, but of course a challenging goal, because at the moment we are only at 30 to 40% in LEO, you would still see a growth of the population. So the conclusion of this diagram, and that's consensus by several space agencies that are organized in the IADC that Michael already introduced, is that you have to do active removal, here abbreviated as ADR. So if you take out 5 massive objects, those objects that have the potential to fragment into many smaller pieces, creating this Kessler syndrome, then you would be in a position to remediate the environment. But only then. So you have to do proper passivation, full post-mission disposal of more than 90%, plus on top active removal. And of course, you may immediately say this costs. Yes, but it's the reality. So what is now the trends that we are seeing? And the trends are, from the space debris perspective, well, come with some difficulties. So we see a drastic increase of the launch rate that you see in the left-hand diagram. This is from our ESA space environment report that we issue every year, and you find on our website. And this is what I said before. We have now a game changer, a revolution setting in how we use space, what we launch. And this is primarily commercial objects, and this is primarily objects arranged in large constellations. And we have to see, we don't know yet how these large constellations affect the space debris environment. And the prediction, as you see on the right-hand side by papers from consulting companies, is the outlook is that it will continue. We see already an increase comparing the last decade to the current decade of more than 500% in the low Earth orbit, of close to 500% in the low Earth orbit to come. Yeah, and the other trend that comes in parallel is the miniaturization of objects. We did an analysis, it's already 3-4 years ago, where we compared the masses to the launch rates. So you see, the increase really comes from satellites that are 150 kilograms or smaller. So those are the dominating objects in the future. And the question is, okay, what can these these nano satellites, what they actually are, do? I mean, they can do a lot in the meantime. They can maneuver, they can be tracked, they can also do some deployment of means to deorbit faster. And I'm not saying that this is bad for the environment, but we have to be aware of the space debris environment, of the precious resource orbit that we are using, and we have to use it in a sustainable way. This is my plea here. And what would help here in the design of satellites, and I know there are some activities ongoing, especially in Graz, helping here, thanks a lot for that, is to make these objects, also the small objects, better tracked or better identified. And not everybody does this. So we used here some launches where a large number of objects were released, several tens up to 100, and we looked how long it took until they were identified and correctly inserted in these catalogs. And you remember, these are the catalogs that we require to do collision avoidance. Without having it in the catalog, we cannot avoid a collision because we don't know where the other object is. And you see some objects or some launch providers do this very nicely, and you have everything in the catalog after a week. Yeah, and for some it takes half a year and you're still at 80%. So there's definitely room for improvement here. Yeah, and coming to collision avoidance, just a few words what we are doing and why this is now getting so expensive. We have a fleet of satellites at ESA that you see here, and in the background you see the density, the spatial density of objects, and it's not a surprise, many of our objects fly where the debris is. So this is a consequence of the orbits that are selected. And yeah, there's now a fleet of around 20 satellites that we do, and we maneuver on average each satellite because of close approach once or twice per year. And that means with 20 satellites, you have every week you have something. So this is a full-time job, and it's not getting cheaper. And the outlook is also not getting better than that. If you look in the statistics, so what we have to avoid, you see a drastic change. On the left-hand side, this is the lowest LEO, where, for instance, the swarm satellites are orbiting. You see now that the vast majority is in this dark blue column, which is due to constellation satellites. So our main job there is to coordinate with other operators to make clear who gives way to the other partner. And that comes on top of the coordination effort for collision avoidance. Right. So we have to change a few things there, and I wanted to bring up a new idea here, which is the idea of space as a resource. So we should not only take into account the probability of collision, but probably we have in the future also consider the consequences. Yeah. And there's something that is developed, is called a space sustainability rating. And this space sustainability rating is a easy to understand, but rather complex to calculate, but easy to understand metric that may help in the future also space traffic coordination, including finding appropriate rules of the road. And that, you will see, is a major topic for the next few years to come. Right, now, what we do at the moment in ESA is a space safety program, and I'll be very brief here because it's not the main task of the talk today. The space safety program addresses all the hazards and threats to our infrastructure in space or on ground. And that comes from either space weather, from natural objects like asteroids or comets, and what comes then from the artificial objects from space debris. And our infrastructure is large, and it's today already very much depending on space applications. It's soon to become $1 trillion economy, as American investment banks have estimated. And it's not only the applications that it creates and the wealth and the economic progress, but it's also a central part of our daily life. Everybody of us is using space applications daily, I would say. And many of us know about this, but many of us also don't know about this. But think back about weather forecasts or navigation some years ago, how this has changed and how everybody uses now space in daily life. And that's why we are depending, and we need to protect this. And space weather is a topic of specific concern here because it can affect large structures on ground, but also in orbit. And in ESA, and this was introduced by Michael already, we had a space situation awareness SSA program that started in 2009, and you see the budget history on the bottom. That was already grouped in these 3 areas. And after 3 periods, in 2019, it was significantly extended to the space safety program, where we also include now large mission developments. And large mission developments are actually 3 of them, here listed under points 2, 3, and 4, that I come to in a second, and the core element and the technology development for automated collision avoidance. So, but first in the core, where we kind of incubate technologies in space weather predictions, but also to host instruments to measure them. Then in the planetary defense, we are developing large telescopes, but also the capability to issue warnings of asteroids coming in. So actually to look up, if you have seen the movie. I think my colleagues were somehow involved as consultants, I understand. And and finally, also in the area of debris, where we have further technology developments, in particular also laser ranging, but also better technology for environment impact assessment, space debris mitigation, and also processing software. Now for the large missions, one of them is going to Lagrange point L5. It's now still called Lagrange, but I think a better name is already in the making. And it would allow much better forecast because it sees, due to the rotation of the sun, evolving events earlier than from Earth. Then Hera is working in consultation with NASA's DART mission, and that was just launched. It will go to the asteroid system Didymos, Moon, and impact there. And Hera would then follow and measure the changes to the orbit and also inspect the impact site. So both depend on each other, of course. And then we have as a third mission Avoidance, which is demonstration of active debris removal. So we have selected an ESA-owned object, Vespa upper stage at 800 times 660 kilometer orbit, and we would launch a satellite, and the satellite will be built and operated by Swiss company ClearSpace. So that's why the satellite is actually also named ClearSpace 1. And it would go there after commissioning, would do a rendezvous, would then use 4 clamps to capture the Vesper upper stage, and then to deorbit to burn up in the atmosphere. And I mentioned already technologies for collision avoidance here as well. Now, in the last 10 minutes, now to the laser ranging. And this one is a new technique. And I looked a bit back to how it started, and I found, in Europe it started in Graz, that we know, but it started more or less exactly 10 years ago with the first measurements published in a paper. And then we did under General Studies program of ESA, a dedicated study for how accurate you can determine orbit from multi-static tracking, and their colleagues from Graz were extremely deeply involved. There was equipment mounted in the Bavarian station in Wetzel, and then we could have the demonstration of the first multi-static debris tracking. And then Michael already mentioned that there was recent highly visible progress in first daylight observations in Graz, and we were also a bit involved in that paper that you see on the bottom left in 2020. And this is so important because if you're only limited to nighttime observations, laser ranging is not the full alternative to radar observations. But if you can progress and do debris tracking also during daylight, it opens a completely new world. So where we stand today? Well, today laser ranging is getting into the satellite operations. It's now seen as an alternative to other technologies to precisely assess the attitude motion, but also the ranging, and it's considered a design of active removal, also servicing missions, as a key contributing technology. And that's pretty interesting because it's quite a career that laser ranging did in the space debris area, and I think the ILS and the Space Debris Study Group, and in particular the groups from the group in Graz, was instrumental to achieve this. So where are we going? I mean, I mentioned already there is now the concept of being able to have a laser catalog. So that means that we can improve the orbits of specific objects for a limited period in time. So that would then help to know the position and the uncertainties much better, so to avoid collision avoidance maneuvers by having just better information. And it will also allow them to track objects so precisely that in the future, by higher power lasers, also momentum could be transferred to, not to active satellites, of course not, but to small, lightweight debris objects. And that would then be an opportunity to nudge by millimeter per second velocity changes, by very small, few meters that you can build up over the course of a few days before a close approach, that the debris goes out of the way of the satellite, not the satellite goes out of the way of the debris. And that's an enormously interesting topic for many operators. Right. I introduced already that we help with our testbed in Tenerife. This is Tenerife. This is how it looks like. We built this together with the company Digos, but mainly out of custom off-the-shelf components. So this is also quite interesting that you basically can buy today laser stations for a certain purpose and have them shipped in a containerized solution and built up in a very short amount of time. This is mainly for the experts in the meeting today. So it's a 80 centimeter ASA telescope. We have as a guiding camera a finger lakes camera. The detector is since the spots working in 532 and 1064 nanometers. At the moment, we can only range to cooperative objects by our Passat laser that we have, but we have planned, and ITT was sent out for upgrades for higher power laser. And we have a stable clock there, so everything works very nicely. We just completed the acceptance. We are now in the process of getting an engineering station in the ILS, and it will stay an engineering station. But we have now the results from the first test, so we are where we want to be in the residuals. So it all looks very good from that perspective. I can go in more details here. But what we are now planning is the upgrades, and the upgrades are for better ranging to debris. So as I said, increase the power, increase the range accuracy, do the daylight tracking based on the research done by you and Graz, and especially also to form networks so that we can hand over the observations to other stations so that we can actually show the suitability for having better collision avoidance predictions, and maybe also re-entry predictions. I know this is a challenging task to track objects during re-entry, but I have not given up hope that we can also master this. As you probably saw, that the increase of launch traffic also leads to an increase in the re-entry traffic. We have to do something about that. And of course, we want to use it as a test bed to also test components for future laser momentum transfer there as well. I may say, and this is a request from my colleagues, that is also planned to use the station for optical comms, but it's not a topic here for today. Right, something on momentum transfer and why this is an alternative. We did 2 studies, one with DLR, TU Munich, and CBK and ALSA in Austria, and the other one on a space-based alternative with Dallas Alenia and the Finnish NLS and the University of Bern. And just to give you the background of this, so I don't think I have to explain how momentum transfer works. So photons go in, and this creates then a resulting force. And we looked into what would it take in a global network. Don't look at all the text. This is certainly too much detail, but we found it's interesting for 2 reasons: for building up and maintaining a catalog, and then do the momentum transfer. Both is to some extent independent as independent users, but of course you need good tracking to do the momentum transfer, as I said. So DLR did a larger system analysis of that and only look at the right side, at the red part, and found that for cataloging you would need several stations globally. Of course, the weather has an effect, but also the access to the orbits has an effect. And if you take a current catalog of about 9,000 objects that should be subject to such interfacing, would not be sufficient to maintain it permanently. So we would need then up to 24 stations in total. But of course, it's not the goal to have it as a complete alternative to the radars. Yeah, but it was interesting to find what we need. And then for the momentum transfer, also look only at the red part, it was found that you could do it. You can have the small nudging effects, but of course you need much more power. But DLR colleagues in Stuttgart confirmed that this is something that is possible technology-wise. It's not available today, but it's clear that it will become available as far as they assessed it. And you would need these 24 tracking stations and 1 momentum transfer station. But to be more efficient, of course, you would need a network of up to 10 of these momentum transfer stations. So the idea is to go further with engineering the technologies, closing the gaps, and build an engineering station in the time horizon of the next 5 years, so to assess the effectiveness of the technology, and then to see whether such a network can be established in the course of the next 10 years. And yeah, and then why not going to orbit? And this was the second study we did, and that was a phase 0 feasibility analysis, where we looked into what would it take to be in orbit in a satellite to illuminate small debris and to nudge them out of the orbit. And what Thales came up with is, yeah, it's quite demanding. It would require a 1 meter steerable telescope in orbit. So this is quite a number, 1 meter diameter. And it would, to be effective, would also need a constellation of 4 satellites. So the result is it's not impossible. It's quite demanding, and there's quite a number of technology gaps, but they recommended to look further into that. And we are thinking now of making a phase A study out of that to understand what would be the schedule for such a technology and whether it would be possible to demonstrate it by 2030. But okay, this is very previous preliminary ideas, as said, and there's a lot of risks in there as well. Right, and now final topic is on the expert center, where also Graz is participating. So the need comes from the fact that we are working with space surveillance systems and external sensors. And if you go to them one by one and coordinate the data acquisition, this is extremely cumbersome, time consuming, and also not error prone. So what is required is actually to have a proxy that takes all these pre-data processing and tasking between the backend catalog system and the sensor. And secondly, it's also interesting from the sensor side to get feedback on the quality of data and whether there are some issues in the setup. And of course, to standardize the data exchange as well. And that's pretty interesting. So we are not coming from zero. It's something that in the ILS exists in a similar setup. You have different levels of sensors that you can have there, and that now the architecture of the expert sensor supports candidate, validated sensor, and also a qualified sensor. And we did this also for laser stations. And as one example, I can show here what we did for the Borowec station in Poland, where we exercised this as an example, how this would look like. So you do a validation campaign and then a qualification campaign, where you then get first the standard deviation for the normal points, and then you can qualify it even more on the success rate for some targets, and you can also improve the accuracy further together with the operators. So this is a quite interesting technology, and we would like to make this available. And we have now a test deployment of the expert sensor in Switzerland, in Bern. And yeah, they are just started to do test operations. Okay, to sum up, and I think I'm nearly in time, what I wanted to tell you today is we are depending on our space-based infrastructure a lot. So they are vital, and I would say they are an indispensable element of our modern societies. But they are space debris, and space debris is a human-made problem, and it's now already a significant cost and also safety issue, first to spacecraft operations, but as it may impact also critical services, also to our modern societies. There is enormous effort in sensor technology in getting a situation picture of the space debris. So we use radars, optical telescopes, in situ sensors, and now emergingly also laser ranging. And all of those have also strong commercialization opportunities. And now more and more companies are stepping in and try to offer data acquisition, but also data interpretation services to the spacecraft operators. We are thinking laser ranging may evolve in a direction where it provides a catalog, but also maybe a stepping stone to momentum transfer using ground-based, and maybe later on also space-based technology. Yeah, and you can only solve the problem through internationally coordinated measures like the space debris mitigation guidelines that exist, but unfortunately are not everywhere followed to a satisfying level. So what is the future? Well, we see already space traffic is undergoing revolutions, and managing space traffic calls for better technologies and also calls for regulation. And in ESA, we have the Space Safety Program doing that, and well, there are quite a number of things to do, and we produced a short movie that is named Time to Act, and by saying time to act is what I would like to conclude with. So thank you very much, and back to Michael.
Yeah, thanks a lot, Tim, for the interesting talk. Yeah, I believe there is room for some questions. So I think we should like call the talk close to be at 1500, and then leave the main discussion items and the main question part to the 15 minutes after 3, but I believe there's some time for questions. Yeah, and from our side, we are very happy to hear about the success of Tenerife Station, and that is actually operating. And we also heard of the good results, and we're also happy that we were able to play a small part within that. And also the future with potential space debris observation is really from the station is really promising, as we see that only multiple stations working together will play a really dominant part with respect to space debris laser ranging technology. Yeah, so I can try. Yeah, maybe someone wants to raise a question via the just main discussion now.
Yeah, I see something in the chat. Should I take them directly now?
Oh yeah, as you wish. I can repeat as well, so it's no problem. Yeah.
No, now I see them. Now I see them.
Okay, perfect.
Impact velocities. Well, impact velocities unfortunately do not scale with size, because you find the debris objects when they are created out of this fragmentation in very similar orbits to the progenitor. So that means every size class you may see in every type of orbit. So therefore,
so then what is actually the reason for these velocities? Is this that you just have crossing orbits?
Yeah,
but or is it the eccentricity maybe? Or I mean, I can see then that it's relatively independent of size. So, but say where is the danger? Is it because of more or less circular orbits which just cross?
Well, the danger comes from the velocity itself. So in LEO you have around 7.5 km/s. So if you get more eccentric, then you get a bit slower. But even if you're still in the 5, 6, 7 km/s, even at apogee, and then the danger comes from the pure impact. So if the other object is also orbiting, you may either have a lateral impact or even a frontal one, and if you or head on. And if you're going head on, you have then 14, 15 km/s. So this is the worst case. And if you look at the distribution in LEO, due to the precession of the orbital planes, that is different. Everything is possible. Every geometry is possible. There's no preferred impact geometry that you can rule out. And yeah, and I said every size class you find in every type of orbit. So you may expect impacts in any situation. The only difference is natural objects. They have different velocities, and that's the only reason how you can how we could discriminate natural objects and artificial objects in our Sentinel-1A case. So from the energy, we could rule out natural objects with a very high likelihood.
Okay, thank you.
It's not good news, but it's as it is. And the second question, this is a small print here, sorry for that. How do we make sure public will not have to pay for the removal of debris caused by commercial launches? A difficult question for an engineer, I have to say. The main problem we see is that orbital resources are not regulated. They are a common good. And what we are running into is something similar to the tragedy of the commons that you also have in other areas. So that you have a common good that is free of use for everybody, and then overuse by some players make the resource unavailable to everybody in the game. And currently, commercial operators are need a license to launch by their countries. So because in the end, under space law, the launching state, how it's called, is absolutely liable for anything related to that mission. So, but this is not collisions; these are not covered. But particularly when it comes to re-entry and damage on ground, this is covered. So, and that's why if you have an authorization to launch from your country, you can do it. That's simply. And if somebody has to clean up, this is just not foreseen today in today's launch regulations. So that's why it's first so important to make sure that mitigation practices are followed. And secondly, we have to find a model to incentivize, because I think space law will not come in time, to incentivize cleaning up or operating properly. It may be that you have to pay a deposit. This is some idea that was recently presented, and you only get it back if you showed that you properly disposed your satellite, or maybe you have to place an insurance that then would pay for the removal. But this is just something under discussion. There's no solution to it yet. I hope this clarifies a bit.
Yeah, so I've seen there were 3 raised hands. So Peter, should we move the question to the discussion in 15 minutes, as we are currently really exactly on time?
Yeah, I would think so. So I would stop the recording now, and I would ask the people with more questions just to reconnect in a few minutes. Just let me stop the recording.